Okay, let's get started. Let me share my screen. Everybody, could you see my screen?
Yes, sir.
Okay. You see, in last class, we started talking about Laplace transform technique applications to circuit problems. And then at the last moment, we were discussing this circuit, and then we ran out of time. Uh, and then probably you remember I was showing you this solution, and then also this was the result. So before discussing further about this type of solution, let's have a look some of the Laplace function. Although you know, but I like to show you once again and then go back to the circuit application. That will make more sense. Uh, Everybody see here, like I am asking, determine the Laplace transform of each of the following functions. Like question number A, ut, that's the function. Question number B, e to the power minus at ut, and while a greater than equal to 0, and C, delta. So therefore, for each of these functions, find out the Laplace transform. So therefore, you all have learned the Laplace transform or currently learning in signal courses, or even you have already covered in math courses, but it's still a little bit few minutes, and then I will jump into the circuit problem. So everybody see the, for example, the first one, ut. So you all know the ut, that is the unit step function. So I am making its Laplace. So what I have to, so we all know the definition of Laplace. You see, this is our definition. That Laplace of function t, which we call function of s, integration of 0 to infinity ft e to the power minus st and dt. So this means we have to multiply by e to the power minus st, that function. That is the definition of Laplace. So here you see exactly I am doing that thing, 0 to infinity. So ut means the value of the function is 1 and e to the power minus st. And then you see the next line, I am making integration. So you all know from the calculus that e to the power minus st means that minus 1 over s will come here, and then this function e to the power minus st. And then put that, because this is definite integral, so then put the limit. So lower limit and then upper limit is infinity. And then you all know how to put these things. First put alpha and then minus, put the 0 value for t. So you will be getting 1 over s. This means the Laplace transform of ut is 1 over s. So I believe you all have done this thing in signal class or in math class. Then see the next. I am just showing you some example of the Laplace just for a few minutes, and then we will look into the circuit problems, how we can apply this knowledge to solve circuit problems. The next function was e to the power minus at ut. Then I am making its Laplace. So then again, integration of 0 to infinity, that e to the power minus at, and then of course you have to multiply by e to the power minus st. So here you see, because this multiplied by this one, so here I am combining these two functions, because this is exponential function, so you can sum up their exponent. This means e to the power, this plus this, and then minus is the common, so s plus a dt. Now again, this is very similar to this one. So then apply that technique, make its integration, minus 1 over s plus a, and then this function as it is, and then lower limit, upper limit. If you apply the lower limit, upper limit, so finally you will be get 1 over s plus a. So therefore, I mean, why I am showing this thing, the goal is that when we will be solving circuit problems, frequently you will be getting this type of function or just ut as the input to the circuit. So because in last class I told To apply Laplace transform technique into circuit problem, the very first task is to convert the time domain circuit into Laplace domain. That is the very first task. At that time, if you see that your input to the circuit is ut, then directly write that is 1 over s. That is the meaning. If you see e to the power minus at in that format, that is 1 over s plus a. The same thing, for example, you solve the problem, circuit problem, and at the end, you have to convert back into time domain. For example, you got some current value or voltage value or whatever for any branch based on the problem. You expressed in S domain, but at last you have to convert back into time domain. And then just an example. For example, this is your voltage value 1 over S plus A, or this is the current value. Then inverse Laplace transform, you have to write down this one. The function of voltage value is e to the power minus 8. Or for example, your result is 1 over S at the end, voltage or current value. So inverse Laplace means you have to just write that is the ut. So everybody, could you follow me what I am saying?
Yes.
Yeah. So I mean, these are pretty simple function. As I said, you already have done this thing. I am just showing you, and I am trying to convey you the message how we will apply this knowledge into circuit problem. So therefore, to solve circuit problem, you don't need to calculate in that way. Just by looking the pattern of the input function, easily you can do. So I mean, I am coming those things. Right? Initially, you can see some chart or table, and that is fine. You can look, and then you can apply those Laplace transform. Okay, then I think I have one or two more problem, and then I will go to the circuit. So here there is a different function. You see, this is find out the Laplace of t multiplied by ut. T multiplied by ut. So in that case, again 0 to infinity t, and then ut value is 1. So I am multiplying by e to the power minus st. Now this is on a special function, integration of t e to the power minus st. If you see the calculus, you see this is the integration of x e to the power x dx. This is a common pattern. Then the result is e to the power, so e to the power infinity over a, sorry, e to the power x over a square in parenthesis ax minus 1. This is the result for this type of function. So exactly I am using this formula here. So function is t e to the power minus st, similar to that one. That's why the result is e to the power minus st over s square. So in this case, S corresponds to A for this basic formula. And then in parenthesis, minus st minus 1. And then put the lower limit, upper limit. So then finally you are getting 1 over S square. Now there is one more, here, e to the power minus j omega t. For example, you got in that format, e to the power minus j omega t. And ut is 1. So then again I am applying the Laplace. So I am getting 1 over s plus j omega. And then there is on specific, and then I will conclude this discussion. For example, determine the Laplace transform function sine of omega t. There might be sine omega t, cosine omega t, because you know that sine omega t means this is the sinusoidal function. If that is the input to the circuit, then what will be its Laplace transformation? So therefore you see at the end, I got this is the result. For sine omega t, you see result omega over s square plus omega square. That omega is that angular frequency. So this means that here you see that I have shown the detailed calculation. So you don't need to detail calculation. If you see your input function is like that, sine omega t, for example, sine of 5t, then this means it is 5 over s square plus 5 square, means 25. Then same thing, I mean, in the reverse way, For example, at the end, you got this result for any current or for any voltage. And then you have to convert back into time domain. So therefore, by looking the nature of the result, so you have to understand that, oh, this is the sine function. So therefore, omega may be like 2, 3, 4, whatever. By looking that on, then you write this one. This will be like sine 5t, sine 2t. That is the result. That's all. So therefore, at the beginning, you have to convert into Laplace domain every component, including the input value to the circuit. And at the end, when you will be getting this type of result, then from there, you have to go back to this one. So that's why what I have done, that from the book, uh, I have taken two tables, you see, Laplace transform pairs. So you see, this is table 14 point on. Currently, we are following chapter 14 from the book. So what you will be doing, you will keep this thing handy in front of you when solving problem. You are allowed to use this one. Initially, you don't need to memorize. So therefore, for example, if you see that your input function in the circuit is del t, del t is called, that impulse function, impulse function. So delta mean it has the value only at the 0 point. Before 0, after 0, there is no value. So that's why it is always 1 Laplace transform. Similarly, if it is ut 1 over s, you see t ut 1 over s squared. So you see in that way everything. Just now we solved sine omega t. If you see sine omega t, then it is omega over s square plus omega square. Similarly, if you get like these are the result you got for any voltage current, then you write down these things to convert into time domain. So meaning that these are the Laplace domain, these are the Laplace domain, but these are the time domain function, time domain function. Similarly, there is other table, table 14.2. If you see this one, the same thing. There are various type of operation of Laplace like addition, multiplication, time differentiation. For example, if it is df over dt, then directly write s function of s minus f 0 naught, initial condition. So in that way, everybody, you will keep this table 14.2 and 14.1 in your hand. It is ready to solve the problem. You can say, even you can use this on during the exam. You are fully fine. So everybody, could you follow me what I'm saying?
Yes.
Yeah, great. Now,
Yeah, that makes sense.
yes,
Please,
everybody.
Anwar.
Yeah, great. So now come back to the circuit problem. Now, here you see, first we have to learn, you see, because our start point was this on this circuit. Okay, so you see here the input is ut. So therefore, easily you can guess this ut means that is 1 over s, Laplace. So, and you see in last class I was doing that on. Ut means that is 1 over s. So in the circuit, I placed it 1 over s. But then in the circuit, there are resistance, inductance, capacitance. So that you have to learn. When I have capacitor, then what will be its Laplace equivalent? If it is inductor, then what is its Laplace form? If this is resistance, then what is its Laplace? So now I will be showing you those things. And you see in the problem, it says assuming zero initial condition. So for this problem, there is no initial value of current or the initial voltage. These are not given. So that time, how to do that, what to do that? And for example, the initial conditions are given. For example, any problem say I0 value is 2 ampere or V0 value is 5 volt. At that time, what to do? So therefore, depending on is it zero initial condition or there is some initial condition, accordingly you have to find out the Laplace, especially for these two components. So therefore, let's have a look those things at first, and then we will come back to the circuit problem. So therefore, yes, so everybody see this thing. Let me make it broad. Okay. Everybody see, this is for the resistance. For example, everybody see, this is in time domain. I have a component resistance. I am applying the AC voltage, which is Vt in time domain. Current flowing is It. So then you all know that Vt is It multiplied by R. Now, here is the Laplace equivalent. When it is Laplace, then I will be using the symbol S. So you see, V in parentheses is current flowing is Is, so R. So it's straightforward that Vs is Is multiplied by R. So this means that when you will be converting time domain into Laplace domain, R, R will not change as it is, as it is. But now say everybody, if it is inductor, look this on the left side. For example, there is an inductor and applied voltage is Vt, current flowing is It. And you see here I have seen I in parenthesis 0, meaning that I am assuming that there was some initial current. This is the initial condition, I naught. So therefore, from this on, what you can write, you see, I have written Vt L di by dt. Okay, now convert into Laplace domain. So this is in time domain. So when you will be converting into Laplace domain, everybody say I am converting. So Vt will be Vs, then L. So what is dit by dt? What is its Laplace? So therefore I was showing you, if you see this one, everybody see this one, df over dt, what is its Laplace? See, s function of s minus f0 minus. You see, s multiplied by fs and then minus f0 minus. So exactly I am applying this on to that there. So you see what I did? It was L, but IT over IT, so S IS minus I0. And then I am just multiplying. So LS IS minus LI naught. And then this is equation number A. Now everybody say, it's a Vs, there is a voltage and it has two components. This is on voltage and minus this term is another voltage. Now I can represent equation A by drawing this circuit. Everybody look this one. So this means this is my Vs, total voltage here, and then there is Is. So Is current is flowing. And you look this one, I have a component which is Ls. This is Ls. And then you see there was minus Li naught. So this means it looks like there is a voltage minus to plus polarity, which is Li naught. So therefore this is the voltage. So this means that now everybody look, left side was your time domain value for the inductor, time domain representation, and right side is your Laplace domain equivalent. So this means when you will be noticing that there is an inductor, this will be your Laplace equivalent. This means L together with a source. And what is the value of that source? L I naught. So this means that then you must know what is the initial condition of I. This means what is the value. Now everybody see, if the initial condition is not given in the problem, then just neglect this one. Just straightforward connect. So in that case, it will be simply SL, SL. But if in the problem initial values are given, then you must use this one as well. Everybody, could you follow me what I'm saying?
Yes. So you're saying the voltage, if no conditions, are just LS?
Yes, yes. So this means that, for example, you know that I was showing you, look this problem. It says assuming zero initial condition. Assuming zero initial condition clearly says, this means that for this one, just apply SL, SL. This means L value is 1. So SL means simply it is S. So in that case, you will be looking what is the problem. Is initial conditions are given or not given? If not given, then simply that will be SL. But if some initial values are given, then you have to choose that format. You have to choose then this one, whole thing that I am saying. So is everybody fine? So soon I will show you some example. I mean, 2, 3, 4 example I will show you. Then it will be clear to you when to use this format and when to use only this one. So therefore, I mean, by looking this one easily you can guess because it is I naught. This means you must need initial condition. So that's why the problem when initial conditions are given, I0 is given, then for L, you must use this format. Okay, then first look and then we are going into problem and I will come back and forth so it will be clear to you. Now everybody say like I developed this diagram based on this equation. See, this was the voltage. Now everybody look, from this expression, let's find out the current value. You see this one, IS. So this means this is IS. So you have to divide either side by LS. So this is VS over LS. And then it is plus sign. I am taking the other side. So plus Li naught over Ls. So therefore, ultimately what you are getting is Vs over Ls plus LL cancel. So I naught over S. Now see everybody look this equation. This is the current expression. So this means that if this is my total current, then it has two components. This is one current and this is other current. There are two current. So how can represent this one into the circuit? So look this one. Here my applied voltage is Vs. That is the current Is is going. And then there is one current here for SL. This means you see, this current is Vs over Ls. So that makes sense. And there is another current source and it is going like downward. So I naught over S. Now you see, so this one again I naught over S. This means when you will be looking that there is initial conditions for current, then you can represent inductor in that format as well. So this means then what we are learning, inductor can be represented either this way or this way when the initial value of current is given. When the initial value of current is not given, this means you don't need to consider, then just remove this branch and or remove this one. It is simply SL. It is simply SL. So now the question is when to use the series combination and when to use this parallel combination. It depends on the problem. It depends on your kind of the choice, but it depends on whether if I choose this one, my circuit will be complicated, or if I choose this one, then my circuit will be simple or complicated. It depends on the situation. So soon I will show you through example, like when to use this format and when to use this format, provided that the initial values are given. So everybody, could you follow me?
Yes.
Yeah. So at this point, I mean, still because I did not go to the problem, you just heard, you just keep in mind that inductor can be represented in that format, either this one or this one, provided that the initial values are given. When initial values are not given, simply LS, simply LS. Now look the capacitor and then I am going to the problem. Now everybody see for capacitor, look this one. For example, they have a capacitor, voltage across it is Vt. This is time domain. Current flowing is It. And I am assuming that there is some initial voltage. That voltage is V0, initial value of capacitor voltage. Now, so you all know this is the representation It, C, dV by dt in time domain. Now convert this on into Laplace domain. So therefore IT is your IS, C is this C. Again apply that Laplace dv by dt. So what you will be getting? S Vs minus V naught. So this is coming from the Laplace transformation of dv by dt. And then you see this is Is, just to simplify, Cs Vs minus Cv naught. So this means that what you are looking here, you are looking that this is the current expression and that current has two components. This is on current and this is other current. Now see, accordingly, everybody look, I have constructed this circuit. This is my applied voltage, current was going. So there will be one current here, but the voltage across it is Vs. So everybody look, so this will be 1 over Sc, because what will be the current here? This Vs over 1 over Sc. So Sc will be in the numerator, and that is actually here. You see, Sc Vs. And then there was another component of current, which is minus Cv naught. This means I am assuming that, this should be the current direction, but it is going, there is minus sign. So you see it is upward and Cv naught, this value. So this means that when you have a capacitor, its Laplace equivalent will be one of this form. So this is one of the form. Now everybody look, if you see that initial voltage is not given, then don't use this one. Only Laplace is for capacitor 1 over Sc, 1 over Sc. Now from there, you see, from equation A, I am constructing the voltage, this one. So Vs, so I am dividing Is over Cs, and then this is going other side, Cv naught over Cs. So ultimately, you see, I have organized here. So this means I have a voltage, and that voltage has two voltage. That voltage has two components. This is on voltage component. This is other voltage component. That I am representing, everybody see, through this one. I have a voltage Vs, and I have one voltage which is 1 over Cs. Current flowing is Is. So look, 1 over Cs multiplied by Is. This is the first component. And this is another voltage 1 over S V naught. So the plus minus 1 over S V naught. So this means that you could represent capacitor either in this format or in this format. It depends on the problem when to use this parallel form or when to use the series form. So soon I will take you some example and then everybody will be clear. And then once again, in both cases, you see there is V naught, V naught. If the initial condition are not given, then just neglect this one. I mean, just it is straightforward 1 over Cs. It is straightforward 1 over Cs. You don't need this branch. So therefore, let's have a look both problems, including the initial condition and without the initial condition, and how we can apply this knowledge into circuit problem. Okay, so therefore, now everybody come back. The last class, the problem I was discussing, once again, I like to show you. So then you will get fun. Now everybody see, this was my problem. For the following circuit, find V naught, assuming zero initial condition. So I have to find out the voltage here. So therefore, I mean, the circuit as it is, so what I have to do, if I can find what is the current flowing through this branch, and then if I multiply it by this component, then that will be my voltage. But I like to apply the Laplace. So the very first step, you have to convert this circuit into Laplace equivalent. That is the very first task. Now everybody see, it was the ut here. So that's why it is 1 over S. Look this circuit, it is 1 over S. Look, 1 over S. Now resistance will not be changed. Resistance as it is 1 and this is 5. And then what was the capacitor? 1 over 3 farad. 1 over 3 farad. But because there was no initial condition 0, so then simply it will be 1 over SC. So that's why look, it is, I have written 1 over SC. You look, the capacitor value was 1 over 3. So therefore 3 is going in the numerator. This is 3 over S. So I put 3 over S. And what was the inductor? Inductor was just 1 Henry and no initial condition. So it will be SL. L value is 1. So simply that is the, S. So you see I have written for 1 Henry, that is SL. So simply S. So I put S. And then this is my circuit. And now based on the problem, what you have to apply, then you apply. Then the rest of, once you construct this circuit, once you make the Laplace equivalent circuit, then apply all the circuit rule that you have learned. And the good thing is that, there is no phasor domain circuit. You don't need to apply the phasor algebra because you see it's the simple, these are the number and then the letter S, that's all. So you can apply fully the simple algebra. It is not the phasor algebra, simple arithmetic algebra. So everybody is fine, like how I constructed this circuit?
Yes.
Yes, sir.
Yeah, so that is the very first task. Yeah. Therefore, I mean, sometimes, for example, what I'm saying, this is the input is ut. It is the simple and that is, 1 over S. But sometimes it will be sine omega t, cosine omega t, or other type of function. Accordingly, you convert into Laplace. And to apply that on, you look those two tables, table 14.1, 14.2, that I was showing you. So you don't need to remember. Initially, you look those things and immediately put what will be its equivalent. And for inductor capacitor, you apply those rules, SL and 1 over SC. Okay, then everybody see, because your goal is to find out the voltage across this one, this component, you have to find out V naught is. So you must need to know what is the current flowing. So that's why you see, I have considered for this loop ion is clockwise, for this one I2S clockwise direction. I am using the loop equation, that method. So therefore for loop 1, this loop, I am getting this equation. This is my source 1 over S and then on plus 1 over S. That is and multiplied by ion and then minus I2 into 3 over S. And for loop 2, I am getting this equation. And then, so you all know how to solve the problem. So there are two variables, ion and I2. You need to find out just I2, then you will be fine. You don't need to calculate ion because you have to find out the voltage here. So therefore, I got I2 is 3 over this thing. You see, this is simply the function of S, although in cube format and square format, but still it's a function of S only. So therefore, now this is I2 and find out V naught. So I have written V naught means S multiplied by I2. That I am doing it here. V naught is 3S over this one. Now this is your result in Laplace domain. I mean, you are done. This is your Laplace domain result. But because the originally question was in the time domain, so you have to find out the time domain value of V naught. That's the thing. You see, it is V naught. It is not V naught S here. So that's why once you get the result in Laplace domain, you apply the inverse Laplace. So that's why now what to do? By looking the format, you have to guess, you have to think how I can represent. What can be my inverse Laplace? Therefore, everybody see in the next line what I am doing. This S is cancelled. In the numerator only 3. But in the denominator, I am looking there is a pattern like AC square plus 8S plus 16. If I can make it 16, then I can write S plus 4 whole square. I could write that. That's why I am doing that. And then because it is 18, so I kept plus 2 here. Then again, by looking that on, I have to think how I can better represent and I can easily apply an inverse Laplace transform technique. So that's why after this one, follow what I am doing. Look this one. Because there was 2 there, so in the denominator, what I did in the denominator, I mean, for this one, I wrote s plus 4 squared, and then for this one, I wrote root 2 squared. So therefore, look, denominator, this one. And then I want to write the root 2 here, therefore I am taking another root 2. And why I did this one? Because there is pattern of sine of omega t. You look, this is like sine of omega t and e to the power minus alpha t. So this means by looking this format, I can easily put what is my inverse transformation, what is my time domain function. Therefore, this is 3 over root 2, and this portion is giving me e to the power minus 4t this one and sine of root. So how I got that one? That thing I was telling you that you have to look that table. Sorry, this one. Everybody see this thing? Look this one. Look this format. This is your Laplace, like omega over, here you see omega, then here it is omega square, and it is s plus alpha square. So if this is the format, then this will be your time domain function, sine omega t multiplied by e to the power minus alpha t, this one. Therefore, by looking this pattern, I was able to tell, okay, its time domain function is this one. Everybody, could you follow me?
Yes.
Yeah. Therefore, you have to match. I mean, what I am saying that, for example, your result could be in any of these formats. Your result could be in any of these format. Definitely, it will match either of the format. Yeah. Then by looking the pattern, you may need to do 1 or 2 more lines, and then you can figure it out. Okay, this will be the time domain function. That's all that I am saying. So that's why that once again, if I go back, by looking this pattern, and that is the reason I am making that pattern, because when I am here, you see, when I was here, then I say, oh, there is a good match. It looks like I can match with like either sine omega t or cosine omega t. So by looking the pattern, you have to guess. That's why everybody, you will make that table 14.1, 14.2, you can make a print, and you can always keep in front of you. And you are allowed to look during homework, midterm exam, anytime. You can look those tables, no problem. So that will help you how to construct. And then over the time, you can remember. You may not need to look those tables. So that, but here it is 2. That's why in the next line, you see, I made like root 2 square. But then because I did root 2, this is like omega. So I have to put root 2 here. But then because I put root 2, then again I have to divide by root 2. And that's the way it will work. So therefore, by looking the pattern, by looking the result, from here you have to think that how I can represent best, so then directly I can apply those rules, inverse transform available in those tables. That's the thing. So is everybody fine so far?
Yes.
Yes. Now let's have a, so therefore clearly you see that in this problem, it was 0 initial condition. Now let's have a look on problem that has the initial condition. Now everybody read this problem. For the following circuit, determine IT for t greater than 0, assume V0 minus is 9 volt. So this means this is a circuit that consists of R and C. So C value is given 1 over 16 farad, but then its initial voltage value is given. Therefore, this time, instead of just this format, you have to think that I have to take into account this one. Therefore, it's not just the capacitor. I have to make some series combination of voltage source so that I can apply this one. So therefore, everybody see from this circuit, how I am constructing the Laplace 1 over S input. So because that was the ut, so its Laplace is 1 over S. So resistance is fine, but now look, I am putting capacitor in that format. What is the format? On over SC, V naught over S. So how I got that on? That is the thing I was showing you. If you see this one, for capacitor, I use this format. I use that format. So everybody look, this format. And now that is the thing. I mean, you might represent in that format, but if you use this format, I mean, because it has the V naught, you can include that initial, but then it is going the parallel circuit. But if you choose this one, this series, then that is matching with that circuit because your circuit is series. Everybody look. Therefore, if you use that series format of the capacitor Laplace equivalent, then whole thing is still series. So it is easy to handle. On the other hand, if you choose the parallel format, then one parallel branch is going. Then you are getting this is one loop, that is other loop. So that's why I said that when to choose, I mean, this format or this format, it depends on the problem and structure of the circuit. If you see that, okay, it's the fully parallel circuit, then you replace capacitor with the parallel branch. That will help you. If you see that it's the series circuit, then use this one. The same thing goes for the inductor. It depends on the nature of the circuit. If it is parallel, then replace the inductor by this format. If it is series, then use this format. So that's why there we are using, you see, series combination of the capacitor. And what will be the this one? This is 1 over SC. And what is this one? V naught over S. And then now put the C value. I think C value was 1 over 16. So 1 over 16, 16 is going in the numerator. So 16 over S. And V naught value you see, this one, initial value, 9 volt. This was given. So I am just putting 9, so 9 over S. So this means now this is my new circuit. I have the source on over S. This is 4 ohm resistance. IS current is flowing. This component is 16 over S. This component is 9 over S. Now you can find out IT. So question was determine IT. So this means first you have to find out what is IS. And once you get the IS, at the end you just convert into time domain. I mean, I am coming into the calculation. So everybody, could you follow me? Do you understand?
Yes.
Yeah. So everybody, please listen to me. I mean, by end of today, I am going to assign you the third set of homework, and all problem will be about Laplace transform. And then the due date will be next Friday, of course, October 2. So you are getting 7 days. And again, I will be further discussing something in Monday's class. I will continue the Laplace. So then you will be fine. So by end of today, first I will upload the homework set 3 on eCourseware, and then I will notify you through email. So that's why everybody please try to understand, then that will easy. So everybody look, once you can construct this type of circuit, I mean from time domain, Laplace domain, then everything is the same. Whatever you apply, superposition theorem, Thevenin theorem, Norton, maximum power, delta Y conversion or whatever, voltage divider, current divider, KVL, KCL, everything is the same. So therefore, the way you applied the Phasor technique to solve all the problem, like homework 2 and something in the exam, same way everything can be solved through Laplace. And you see the essence or the beauty or the good characteristics of Laplace, you don't need to deal with the Phasor algebra. You see, there is no angle. That is the main thing. So therefore, once you can convert the circuit, you apply the circuit rule and the simple algebra, because it is the function of S, simple algebra. And then you find out what you need to find out. And at the end, you just convert into time domain. That's all. So therefore, everybody see, for this circuit, you have to find out the IS. So what I am doing, because this is a series circuit, so this is my source 1 over S, and then you 4 multiplied by IS. This is the voltage drop here. And then this one is 16 over S multiplied by Is. And this is directly the voltage source, so 9 over S. So from there, you see, I got, this is the result. Is is minus 2 over S plus 4. So then how I got the result that I am showing you, I am simplifying. You look, I am taking the Is common factor here, Is. So there's 4 plus 16 over S, and then this 1 over S. I am transferring this on the other side, minus 9 over S. So I got minus 8 over S. So therefore, from here, I simplified this one, 4S plus 16 over S. This is minus 8 over S. So finally, I am getting ISH minus 8, so minus 2 over S plus 4. I mean, which I showed here. And then you apply the inverse transform. So therefore, IT is this minus, this is 2. S plus 4 means e to the power minus 40 ut. You are done. That's the answer in time domain. So everybody, do you understand?
Yes.
Yeah. So therefore, I mean,
I have
sure, please go ahead.
one question with this example compared to the last example.
Mhm.
You omitted putting the UT. Is that,
Oh.
I mean, we understand that UT is 1 or 0, but like, do we have to always put the UT on the end?
Yeah, it is, you are right. So in the last problem also, please put UT. Yeah, always please put UT. Yeah, so you can put UT. Yeah, and I recommend you to do that. In the last time, I think I did not put, but please put UT. Okay, therefore look one more problem, then it will be much clear to you. Yeah. Everybody see this circuit. For the following circuit, determine V naught. So, and then assume V naught is 5 volt. Therefore, you can see, because the capacitor initial voltage is given, easily you can guess that, okay, which format you have to choose. Now, before doing anything, everybody see, this is, you can easily guess that we have to use the initial condition. Now, because this is the, you see the parallel circuit, this is parallel, parallel, parallel. So it is better to represent this capacitor into parallel format. You see, I have used capacitor and that the current source. So therefore, so how to get there? Therefore, you have to remember this on this slide. You look, capacitor can be represented either this format or this one. So this is the parallel format. What is the parallel format? Capacitor is 1 over SC, and this current, this will go, you know, the upward, and that is C V naught. And V naught is your initial condition. Therefore, here, I mean, of course, you could pick this one, but I picked this one, I chose this one, because that was the nature of the circuit. So therefore, like this is parallel, this is parallel, this is parallel, and I can put one more parallel, so I can apply parallel technique here. That will be your motivation, that which form to choose. So therefore, everybody say, first convert this one into Laplace domain. So therefore, here everybody look, the input was 10 e to the power minus t ut. So this means it will be 10 over s plus 1. So therefore, again, if you see that table 14 point on Laplace transform, when it is e to the power minus t, then that is 1 over s plus 1. So I got 10 over s plus 1. And then 10 ohm as it is. See, these two are the resistance. Now, right side, look, this is a current source, 2 del t. But del t is called impulse function. Its Laplace transform is 1. So this will be simply 2. So therefore, that is simply 2 ampere. Now the capacitor, that one, because I have to include this one. So I am decomposing, I am writing in that way, this one. So which is 1 over SC. So S, and then you look, C value was 0.1 farad, 0.1. So 1 over SC, then 0.1. So 10 is going in the numerator. So 10 over S, and this is that C V naught. So therefore V naught is 5, and then C was 0.1. So 0.5 ampere, but the direction will be upward. So therefore now this is my circuit. So everybody see, this is left side is a voltage source, 10 over S plus 1. And you know, this is the total current. Current is going here. I have given direction. Current is going there. But this is going upward and this was going upward. Those are given. Now, what was the question? Question was determine V naught T. What is the voltage across this one? That's your task. So that's why, you know, I am simplifying. I want to apply nodal analysis at the top node. So that's why here I have assumed that this point voltage is V naught. This means this voltage means that is the point, this. Here the voltage is V naught. Now what I am doing? I am applying, you know, the current rule, Kirchhoff's current law, like current entering here and then current leaving there. So you see, this current is entering, this current is entering there, this current is also entering there, but then current is leaving this one and this one. So this means this current plus this current plus this current, that will be equal to this current plus this current. So everybody, could you understand what I am saying?
Yes.
Yeah, so just the nodal analysis. Therefore, if you see, now you see, what is the current here? So how we will know that? Because this is voltage source. The current, these all are the like current, but this is the not the current, this is voltage source. So the what I am doing, everybody look here. This is my voltage. You see, what is the voltage here? Which is that I assumed V naught is. So therefore, this voltage minus this voltage divide by 10. That is my current here. You see, that I did. So 10 over S plus on this one minus the voltage here, which is V naught is, divide by 10. So that is my current here. So that current plus this one is going there 0.5, this 0.5, and then this 2, this 2. That equal to, what is the leaving current? This one. What is that? V naught over 10, this one. Plus, what is the current here? V naught over 10 over S. So just this is the KCL, Kirchhoff's current law. And then you say, I am simplifying, see all the calculation. Finally, I got, this is V naught. 10 plus 25 S plus 25 over S plus 1 into S plus 2. Now you see, in this format, now it is difficult to construct what will be the time domain function. So here you have to apply some technique. For example, here the technique is apply the partial fraction rule. Partial fraction. So therefore, that was my B naught. So what I am doing, assuming this one is A over S plus 1 plus B over S plus 2. So now I have to get the value of A and B. So you all know the partial fraction. So I got A10, I got B15. And then I am plugging this AB value here. Sorry, here. So this means I got V naught is 10 over S plus 1, 15 over S plus 2. Once I get this format, then it is easy to apply because I know this one is e to the power minus 1t and this is e to the power minus 2t. And then ut. That's my answer. Everybody, could you follow me?
Yes.
So now probably you have learned this thing. I mean, of course, you know, from the math viewpoint, but I think signals and system course you have learned. And instead of partial fraction, probably I think Dr. Jacob might have used, it is called cover-up method, right? Or it is called residue method. So therefore,
Yes.
yeah, you know, therefore I also recommend you to use that one, or I mean, whatever format you prefer, you do that. Yeah. Here I just use that simple partial fraction rule, but of course you can use that cover-up method, which is called the residue method as well. From the viewpoint of math, you can apply whatever technique you feel comfort, and then, but you must be getting the same result. So this will be the nature of the Laplace application to circuit. Therefore, everybody say, what is the main benefit of this method? Now everybody remember your RLC circuit chapter, RLC series circuit. So when there was one initial condition, what you did, how you solved the problem. Like you remember, you chose like either over damped, under damped, and critically damped, right? And then you chose the equation and apply the what is called differential equation, and then find out the value of A1, A2, use the initial condition. It was very lengthy and cumbersome and somewhat difficult. So what is Laplace doing? Just once I can construct the circuit in that way, then inherently it is taking into account the your initial condition. So everybody, do you understand what I am saying?
Yes.
So, yeah, because you are representing the capacitor, you are decomposing the capacitor in that format. So that's why that is including your initial condition. That's why here you are not worried to apply those rules that you did in RLC transient chapter, even though there is initial condition. So that's why it is the easiness, it is the beauty, and this is the significance of applying the Laplace transform. That's why Laplace transform is the most powerful technique in electrical engineering to solve the circuit problem, both electrical and electronic circuit, application of the Laplace. Therefore, the problem we solve through the phasor, everything you can solve with the help of Laplace. Everything is possible. But sometimes in job market you will be noticing that some circuits, some components are available in phasor format. That's why you have to understand the phasor. Okay, it will not be telling, okay, you do in Laplace or phasor. Circuit will be given in the phasor domain. That's why you have to learn the phasor. That's why we learned it. But if nothing is specified, okay, solve this problem, it did not say in time domain or phasor domain, then you can do the Laplace method. You can apply easily the Laplace method. I think based on this knowledge, you are able to solve the any problem now. As I said you, first you have to convert into Laplace domain by applying those methods. You have to convert source, inductance, capacitance into the appropriate Laplace form. And then you see what is the problem, and you just apply the normal rule that you already know. And once you get a good format, then you see how you can apply and how you can get back into the time domain. Think that how you will apply the inverse transform technique. That's all. So is everybody fine?
Yeah, doing good.
Yeah, so therefore what I am going to, as I said already, I am going to assign you the third set of homework. You will be looking, there are 7-8 problems in homework set 3, and then you will start solving. The due date is October 2, the next Friday. So you'll be fully fine. But you might not be able to solve all problem, until I give another lecture on Monday. So probably you will be able to solve 50%, 60% of the problem based on your today's knowledge. But I will be going further. I will be discussing transfer function that I will be covering in Monday. After that, you all are able to solve all the problems in the homework. Therefore, once I notify you, you start looking, you try to solve some of the problems during weekend if possible, and then wait until Monday, my next lecture, and then you will be able to solve all the problems. Okay, so I think already we are over. So does anyone